Although the science of chemistry may at times seem overwhelmingly complicated, it's comforting to know that all matter, that is, everything that has mass and occupies space, is composed of only 112 elements, with only 92 of them occurring naturally. In fact, the 8 most common elements in the Earth's crust make up over 98% of its mass. The names of these elements and the compounds they form is essentially the language of chemistry and is the focus of this program. In an earlier program, you learned that an element is a chemical substance that cannot be separated into simpler substances by chemical processes. Elements are composed of atoms, and the atoms of different elements are distinguished by the number of protons in their nucleus. Several elements can combine chemically to form compounds. A compound is a substance that contains 2 or more elements combined in a fixed proportion. In this program, you'll learn how elements and compounds are named according to rules set forth by international commissions that regulate the science of chemistry.
Often, elements are referred to as being in an atomic or elemental state. An element in the atomic state refers to a single atom, such as atomic silver or atomic uranium. Several elements are found only in the molecular state. The molecular state describes 2 or more atoms that are chemically bound together and act as a unit. You may think of these elements as coming only in pairs, and for that reason, they're referred to as diatomic molecules. Gases, such as nitrogen, oxygen, and hydrogen, rarely exist as single atoms. These elements are written as N2, O2, and H2. It is common practice to refer to these elements simply as molecular nitrogen or molecular hydrogen. In addition, oxygen can also form a molecule consisting of 3 atoms, O3, a molecule commonly known as ozone.
The term nomenclature means a system of names. Chemical nomenclature specifically refers to the naming of chemical species. A chemical species can include elements, ions, or compounds. Elements combine naturally or are combined by chemists in a laboratory to form millions of different compounds. Without a system based on standardized rules for naming these compounds, scientists could not efficiently communicate. There would simply be too many names to remember. To alleviate this problem, rules and procedures regulating chemical nomenclature have been established by the International Union of Pure and Applied Chemistry. The naming of elements, ions, and compounds follows strict guidelines to ensure that all scientists, regardless of their national language, can effectively communicate by learning and using one standardized chemical language. Although compounds are named systematically, the elements were not. The names of the elements are derived from a wide variety of sources, and the history behind these names is fascinating. Ancient Greek and Roman philosophers, relying on imagination and a common sense approach to understanding the natural world, named the first documented elements. For example, the element we know as gold was first called aurum. Aurum is a Latin term meaning shining dawn, which describes the element's golden luster. Many common and easily purified elements are named after the source from which they are obtained. Natrium, Latin for sodium, means the sea, from which sodium salts are easily collected. Carbon is derived from the Latin carbo, meaning charcoal. Potassium was first extracted from boiled ashes. Its name is derived from the English term potash. Other elements are named for their appearance. Cesium is taken from the Latin term meaning sky blue, and chromium from the Greek term for colorful. Chlorine, another Greek term, describes this element's greenish-yellow color. Some elements are named after famous people, usually scientists. The element Einsteinium, produced in 1952, is named in honor of the famous 20th century physicist Albert Einstein. And curium is named in honor of Pierre and Marie Curie, best known for their work with radioactivity. Nobelium takes its name from Alfred Nobel, who established the distinguished Nobel Prizes. Fermium is named for Enrico Fermi, a nuclear physicist. Mendelevium is named in honor of Dmitry Mendeleev, the Russian chemist and architect of the modern periodic table. Several elements, such as francium, californium, and germanium, are named after the location or country where they were first discovered. Copper is derived from the Latin term cuprum, which refers to the island of Cyprus. Ruthenium is Latin for Russia, where this element is found.
Some element names describe the physical properties of those elements, and others are named more creatively. The chemical symbol for gold, Au, reflects its Latin name, aurum. Aurum means shining dawn and describes the brilliant luster of this element. Many elements reflect some obvious physical property. Osmium is derived from the Greek term osmi, meaning smell, and bromine from the Greek bromos, meaning stench. Manganese is derived from the Latin term for magnet and refers to the magnetic properties of rocks containing manganese metal. Several elements, such as thorium, are named after mythological gods. Thor is the Scandinavian god of war. The elements plutonium and mercury are named for the Greek gods Pluto and Mercury. Cobalt is derived from the German term Kobold, meaning goblin or evil spirit. As you may gather, the history behind the element names really is interesting, and you may consider consulting a handbook of chemistry for more information on this topic.
As the elements were discovered and their chemical properties determined, chemists needed a convenient way to organize them, as well as any information known about them. Modern chemists arranged the elements based on their atomic number, as well as other properties, in a periodic table of the elements. Currently, there are 112 recognized elements, though this number may change as new elements are created by scientists. Though the periodic table and its organization is further explored in another program, we shall discuss, for our purposes, how all elements fall into three broad categories: metals, semimetals, and nonmetals. Elements are categorized most broadly as either metals, nonmetals, or semimetals. Metals occupy the left-hand side of the periodic table and are highlighted in blue. Metals are the most common class of elements. 88 or so of the 112 known elements are metals. Metals tend to lose their electrons, are usually shiny when clean, can be formed into shapes, and are good conductors of heat and electricity. The 17 or so nonmetal elements are found on the far right of the periodic table. The nonmetals, shaded in red, are poor conductors of heat and electricity. and are dull or cake-like in appearance. Many of the nonmetals are gases or liquids. Hydrogen gas is certainly a nonmetal, but due to some other interesting properties, this element is located above group 1A on the table. There are about 7 elements classified as semimetals. The semimetals display properties in between metals and nonmetals, depending on a variety of conditions. Almost all chemistry relates to the structure and behavior of the atom. Although it has long been suspected that matter is composed of atoms, only recently has the structure of the atom been determined. Atoms are composed of 3 subatomic particles. The core of the atom, known as the nucleus, is composed of positively charged protons and uncharged neutrons. The nucleus is surrounded by a negatively charged electron cloud. These electrons are in constant motion around the nucleus. So far, we have discussed elements and compounds that are electrically neutral. In other words, atoms in the elemental state and compounds formed from elements do not carry a charge. Ions are atoms or groups of atoms that are electrically charged. Ions can be either positively or negatively charged. You may recall that electrons are negatively charged atomic particles. The gain and loss of electrons is responsible for the charge of an ion. Positively charged ions are called cations and indicate a species has lost one or more electrons. Negatively charged ions are called anions and indicate that a species has gained one or more electrons. Chloride ion and hydroxide ion are common examples of anions. Sodium ion and ammonium ion are good examples of cations. The charge on an anion indicates how many electrons have been gained. Can you see how gaining an electron would result in a negatively charged atom? Conversely, the charge on a cation indicates the number of electrons that have been lost. Does it make sense that when a neutral atom loses a negatively charged particle, the result is a positively charged atom?
Ions composed of just one atom are called monatomic ions. The term monatomic cation describes a single positively charged atom. Monatomic cations are usually metals that have lost one or more electrons. Monatomic cations are easy to name. When naming monatomic cations, simply state the name of the element and add the term ion. For example, a sodium atom that has lost one electron is named sodium ion. Likewise, this magnesium atom that has lost 2 electrons would be named magnesium ion. In describing the charge on these 2 atoms, we would say sodium has a +1 charge and magnesium has a +2 charge. Naming monatomic anions is just as easy as naming the cations. Anions are formed from nonmetal elements that tend to gain electrons. To name an anion, simply replace the ending of the root element with the suffix "ide." For example, a negatively charged fluorine atom is a fluoride ion. Can you see how the former suffix "ine" was replaced by "ide" to indicate the anion? Likewise, a bromine atom with a negative charge is named bromide ion. Let's try one that's a little more difficult. How would you name the oxygen anion? The original "gen" ending is replaced with the "ide" suffix, giving us the oxide ion. And the same goes for nitrogen, resulting in the nitride ion.
Unlike sodium and magnesium in the previous examples, many elements are capable of forming several ions with various charges. To provide a means of naming the various charges of a single element, two systems have been devised. One system, the stock system, uses Roman numerals to indicate the particular charge. For example, an iron atom may be +2 or +3. Iron 2 ion is the name for the ion with a +2 charge, whereas iron 3 ion describes an iron atom with a +3 charge. Sometimes symbols do not reflect common names because the symbol reflects an ancient language name. The chemical symbol for iron, Fe, reflects the Latin name ferrum for this element. Let's look at another example. Cobalt +2 is written as cobalt 2 ion. And not surprisingly, cobalt with a +3 charge is named cobalt 3 ion. Can you see how the various charges on manganese are named? As mentioned previously, there are two ways to name ions capable of carrying multiple charges. When an element is capable of only two charges, such as iron or nickel, the classical method of naming ions can be used to distinguish between the two ionic states. The classical method uses the root of the element and the suffix "us" for the lesser of the two charges, and the suffix "ic" for the greater of the two charges. For example, an iron atom with a +2 charge would be ferrous ion. An iron atom with a +3 charge is the ferric ion. Observe how the two ions of cobalt are named with this system. Now that you have learned both the stock and classical systems, compare how several different ions are named using these systems. When two or more elements combine, they form compounds. For example, magnesium oxide is a compound consisting of 60% magnesium and 40% oxygen by mass. Although several elements, such as silver, gold, and carbon, may be found naturally in their elemental form, most elements are so reactive they are only found in compounds. Although there are only 92 naturally occurring elements, they combine in an almost endless array to form millions of compounds. Most languages contain names for common chemical compounds. Some English terms you may be familiar with are water, rust, glass, and bleach. The name of a compound describes several features of that compound. The most fundamental components of a compound are the atoms and the ratio of those atoms that form the compound. A chemical formula shows the number and kinds of atoms present in a single unit of any compound. A subscript is a small number written next to and below elements in a compound and indicates the number of atoms of that element in the compound. By observing the following chemical formula for water, we can determine the compound consists of 2 hydrogen atoms for every 1 oxygen atom. By convention, the subscript is omitted when there is just 1 atom of that element, in this case oxygen, present in the compound.
Let's look at another example. Sodium hydrogen carbonate, commonly known as sodium bicarbonate. Sodium bicarbonate is a common ingredient found in antacid tablets. Sodium bicarbonate reacts with other compounds within the tablet to produce the familiar fizz when dissolved in water. The chemical formula for sodium bicarbonate is NaHCO3, which describes a compound consisting of one sodium atom, one hydrogen atom, one carbon atom, and 3 oxygen atoms.
Some common compound names that were previously mentioned were bleach, water, glass, and rust, and we could have continued to name many more. Water is technically dihydrogen monoxide. Rust is iron 3 oxide. Glass is silicon dioxide, and bleach is sodium hypochlorite. Languages evolve terms for compounds that are commonly utilized or encountered. However, names such as water, rust, and bleach tell us nothing about the chemistry of these compounds. Furthermore, the world's languages prescribe their own terms for these compounds, which makes global communication even more difficult. For example, dihydrogen monoxide can be referred to as water, agua, or nook, depending on which language is being spoken. To avoid confusion among scientists of different nationalities, the chemistry profession has established a system of rules for naming compounds and adheres to them on a global basis. Chemical compounds are classified as either organic or inorganic. The study of inorganic chemistry leads to the study of organic chemistry. The differences between these two types of compounds are so significant that chemistry courses, textbooks, and academic degrees are specialized in either organic or inorganic chemistry. Organic chemistry is life-based. Organic chemistry describes the chemistry of living or once living organisms. Organic compounds, and there are millions and millions of them, are usually centered around the versatile carbon atom. Some examples of organic compounds you may be familiar with are sugars and proteins. Examples of organic compounds you may not associate with living things are gasoline, alcohol, and aspirin. Introductory chemistry focuses on the study of inorganic compounds. Inorganic compounds may contain carbon, but most of them do not. Inorganic compounds are not made by living organisms, but contribute to life in many ways. For example, most living organisms require oxygen and are composed to a large degree of the inorganic compound water. This program, designed for the beginning chemistry student, will concentrate on the naming of inorganic compounds. Inorganic compounds can be divided into ionic and molecular compounds. Ionic compounds are composed of 2 or more ions formed from metals and nonmetals. Ions combine in a process known as ionic bonding, which results in neutrally charged ionic compounds. Molecular compounds are formed from nonmetals that combine in a process known as covalent bonding. Bonding between atoms is a separate topic in chemistry and will be covered in another program. Molecular compounds are easier to name than ionic compounds, so you will learn to name them first. Molecular compounds contain only nonmetals. Molecular compounds are sometimes referred to as binary covalent compounds. The term binary means 2 parts, and covalent describes the particular type of bonding that takes place between the 2 atoms. To name a binary molecular compound, simply specify the number of atoms of each element using a numerical prefix and add the suffix "ide" to the second element in the molecule. If there is only one atom of the first element, no prefix is used, since a 1 is understood. Let's try an example. CO2 would be described as carbon dioxide. Carbon refers to the single carbon atom, and dioxide describes the two oxygen atoms of the second element. Try this one, N2O5. Can you see why this compound would be named dinitrogen pentoxide? When elements combine to form compounds, metals tend to lose electrons, forming cations, and nonmetals tend to gain electrons, forming anions. A compound that is composed entirely of ions is called an ionic compound. Again, the term binary means two parts. Binary ionic compounds contain two ions, one cation and one anion. For example, sodium chloride is a binary compound formed between the sodium cation and the chloride anion. These opposite charges combine to form a neutral compound. You can think of the positive and negative charges as canceling out. To name a binary ionic compound, simply write the name of the cation followed by the name of the anion. As you can see, the term ion is omitted because binary ionic compounds, like all compounds, are electrically neutral.
Let's practice a little more naming binary ionic compounds by determining just how the cations and anions assume their charge. Magnesium oxide is the compound formed between the elements magnesium and oxygen. Magnesium, being a metal, readily gives up 2 electrons to oxygen, which in turn gains those 2 electrons. On your screen, you'll see an overall exchange of 4 electrons, because the balanced equation contains 2 atoms each of magnesium and oxygen. This exchange of electrons forms the magnesium cation and the oxygen anion. When the ions combine, the charges on the individual atoms cancel out, resulting in no overall charge on the compound. Therefore, no charge is indicated when writing the chemical formula. Can you name the following compound? Ca3N2. When calcium and nitrogen combine, calcium metal gives up 2 electrons to gaseous nitrogen, forming the cation, calcium ion, and the anion, nitride. As a result, calcium and nitrogen form the calcium nitride compound.
Whereas binary ionic compounds are composed of just 2 ions, one anion and one cation, other compounds contain several ionic species. These compounds are called polyatomic ions. Polyatomic literally means many atoms. And by now, you know the term ion indicates a charged chemical species. Polyatomic ions are tightly bound groups of atoms that behave as a unit. One example of a compound containing polyatomic ions is ammonium nitrate, composed of the polyatomic ions ammonium and nitrate. Ammonium nitrate is a fertilizer added to nitrogen-depleted soils. Another example of a compound containing polyatomic ions is sodium carbonate, composed of a sodium ion and the polyatomic carbonate ion. Keep in mind that sodium is not a polyatomic ion. It is a monoatomic cation, but combines with a polyatomic anion to form a polyatomic compound. Some polyatomic ions, like ammonium, retain their historical name and must be memorized. However, most polyatomic ions follow established naming conventions. Most polyatomic ions contain oxygen atoms and are referred to as oxyanions. Oxyanions serve as good examples for naming polyatomic anions. When there are two members in a series of oxyanions, the ion with the least number of oxygen atoms is given the suffix "ite," and the ion with the most oxygen atoms is given the suffix "ate." This is a series of two anions with different oxygen counts. In addition to sulfur, the ion on the left contains 3 oxygen atoms. The ion on the right contains 4. The ion with the fewer number of oxygen atoms is the sulfite ion, and the ion on the right would be a sulfate ion. When there are 4 members in a series of oxyanions, the ion with the fewest number of oxygen atoms is assigned the prefix hypo. Hypo is a Greek term meaning below or less than. The ion with the most number of oxygen atoms is provided with the prefix per, which means above or excessive. Referring to our rules, we will work from left to right on your screen. The ion on the far left contains the fewest oxygen atoms, and in addition to assuming the "ite" suffix, it is assigned the prefix hypo, meaning least. The 2 middle ions are treated like a series of 2 and are provided with the suffixes "ite" and "ate," respectively. The last ion contains the most oxygen atoms in this series, and therefore is given the prefix per, meaning more than. This ion assumes the suffix "ate" because it is nearest the chlorate ion. Several polyatomic ions contain a hydrogen atom. When the hydrogen atom precedes the other elements, the ion is named by simply adding the prefix hydrogen and naming the ion. If there is more than one hydrogen atom, the number of hydrogen atoms present must be indicated in the name. Take, for example, hydrogen carbonate. Try another one. Can you see why this ion would be named dihydrogen phosphate? The phosphate is the anion, and since there are 2 hydrogens, the prefix di is applied. Ionic compounds that contain polyatomic ions may contain several different atoms, but are named in a similar manner as binary ionic compounds. You may recall that binary ionic compounds are named by first stating the cation, followed by the root name of the anion, and the suffix "ide." When naming compounds containing polyatomic ions, first name the cation, followed by the polyatomic anion. A good example of a compound containing a polyatomic ion is copper 2 nitrate. How do you know the charge on the metal is +2? By knowing the charge on the polyatomic ion and knowing the compounds are electrically neutral, you can deduce the charge on the cation. Let's see how the charge on the cation is determined. because the anion nitrate has a -1 charge, and compounds have no overall charge, the charge on the copper atom must be +2. Since the copper cation can be +1 or +2, the specific charge must be indicated in the formula name using Roman numerals. So the cation is written as copper-2. The ion is the nitrate ion. So the name of the compound is copper-2 nitrate.
Another example of a compound containing a polyatomic ion is calcium phosphate, which is found in bones and adds to their strength. To name this compound, first name the cation, which in this case is calcium. Calcium is only capable of assuming one charge, +2. If an atom is capable of forming only one charge, the charge is not stated in the chemical name. Next, we name the polyatomic ion, which, as you learned earlier, would be phosphate. Finally, combining the names of the cation and anion gives us the name of this compound, calcium phosphate. Observe, once again, how the negative and positive charges balance, resulting in a compound with no overall charge.
Acids are compounds composed of hydrogen ions and anions. The atomic structure of hydrogen is different from all other atoms because the hydrogen nucleus does not contain a neutron. A hydrogen atom is simply one proton orbited by one electron. So a hydrogen ion that has lost its electron is simply a proton. Acids dissolve in water, resulting in a separation or dissociation of the hydrogen ion and anion. Therefore, acids can be thought of as compounds that release protons when dissolved in water. The rules for naming acids depend on whether or not the acid contains oxygen. If the acid does not contain oxygen, the name of the acid comes from the root name of the anion, in this case, chlor, from chlorine. The acid's name includes the prefix hydro, the root name of the anion, the suffix ic, and the word acid. In this example, the chemical formula HCl describes a compound known as hydrochloric acid. When an acid contains oxygen, the suffix of the anion is replaced with either ic or us. Anions ending in ate are replaced by the suffix ic, and anions ending in ite are replaced by the suffix us. For example, the nitrate ion containing a hydrogen atom dissociates in water, forming nitric acid. Again, the word acid follows the name of the compound to describe a proton donor dissolved in solution. How would you name the acid formed from the nitrite ion? Because nitrite ends in ite, the acid is given the suffix us, and the compound would be named nitrous acid. Now that you know how to name the two categories of acid compounds, you should review the following examples. The compounds to the left of your screen do not contain oxygen, so the name of the acid comes from the root name of the anion, such as bromine and fluorine. The acid's name includes the prefix hydro, the root name of the anion, the suffix ic, and the word acid. When an acid contains oxygen, the suffix of the anion is replaced with either "ic" or "us." Anions ending in "ate" are replaced by the suffix "ic", as in phosphoric acid, and anions ending in "ite" are replaced by the suffix "us", such as hypochlorous acid. In review, elements are composed of atoms, and the structure of an atom is responsible for the properties of elements. In this program, you investigated how several of the 112 known elements were named based on appearance, chemical properties, and folklore. Then, you looked at how these elements are categorized and arranged in the periodic table. Chemical compounds, such as water, are defined as two or more elements that are chemically bonded together, and you learned how they are classified as either organic or inorganic. The need to standardize the naming of compounds became obvious as more and more chemical compounds were discovered or produced, and you learned how to name several types of inorganic compounds. Standardized methods for naming chemicals allows the scientific community to communicate effectively. The system composed of methods, rules, and guidelines for naming chemicals is known as chemical nomenclature. As a result of viewing this program, you have learned to recognize and name many commonly encountered chemical species. You now know that most chemicals are known by their scientific name, but several compounds, such as water and ammonia, are referred to by common names. Understanding chemical nomenclature is difficult at first and requires a lot of practice. The interactive tutorials and tests provided in this program will allow you to practice and improve some of the skills needed for mastering chemical nomenclature.